for organizing this nice workshop. Yeah, so I will talk about some recent results about multipartite entanglement. And yeah, basically, I will first start with a quick overview of resource theories, although, yeah, many talks, so we'll do very, very quick because I guess most of you know what it's about. So in a resource theory, we typically talk about free states and like states that are not free are called resource states. And basically, we also consider free operations that map free states into free states. And yeah, and one of the questions that we will address in this talk is about convertibility of states. So after you have defined all your free states and operations, you can ask, okay, can you convert a state rho into another state sigma with this free operations? Yeah, and basically the theory that we will look into is the theory of entanglement, where the free states are separable states. And okay, the free operations can be LOCC or can be some other sets that we will also look into. Yeah, so basically, let us now quickly review the theory of bipartite and multipartite entanglement. So I call it here a canonical resource theory of entanglement. This is the theory where your free operations are LOCC, right? So you have, in the bipartite setting, you have Alice and Bob, and they can do measurements here locally. They can also exchange their outcomes. And but in yeah, as you have also seen in this workshop, there are some like LOCC was the first set of operations that was maybe, and is also operationally very nice and intuitive to understand. But there have been other classes defined over the last decades, I would say, for various reasons. So one class is, for example, LOCC with a sublinear number of singlets. So you allow the parties to do LOC, but also to add a sublinear number of singlets. Why sublinear? Well, because you don't want to change your rate, or at least you don't want to trivialize your conversion rates. Well, another class is the separable operations. Well, essentially, yeah, it's got also a super class of LOCC. There, we just a few minutes ago, we had a talk about essentially PPT operations, or operations that preserve the positivity of the partial transpose. Also non-entangling operations, so CPTP maps that essentially map separable states into separable states. Also, this is a lot. I mean, this is probably almost the largest class of operations that you might allow, although you might even allow adding a little bit of entanglement, as long as it kind of disappears asymptotically. We will talk about it a bit later, also in more detail. Yeah, so this was introduced essentially by Martin and Fernando. Yeah, and if you look at all these operations, so if you you could ask, okay, what do they have in common? So what is kind of the minimal, what is kind of the minimal requirement that they all fulfill? And it's not that they do not create entanglement, because these operations, they can create entanglement. I mean, also PPT preserving operations can create entanglement. So one of like probably the core feature that they all share is that they lead to bounded conversion rates. So if you have some entangled state rho, well, if you have two entangled states, rho and sigma, and you look at the asymptotic conversion rate, then it's always bounded. So, and that essentially means that it's a non-trivial, that each of those lead to a non-trivial theory of entanglement. So all of them lead to some sort of entanglement theory, and each of them is non-trivial because the rates are bounded. And okay, the rate to go from rho into a separable state is infinite. Just saying that that just means that separable states are free in that theory. So, yeah, but yeah, so basically And this is exactly kind of the difficulty if you try to set up a new framework. For example, here, if you allow to add a little bit of entanglement, you kind of the difficulty is to find a framework which still preserves leads to bounded conversion rates. Because if you add too much and if you allow for the operations to do too much, then you can easily end up with a framework with unbounded rates, and this is then a problem. Okay, now let's talk a little bit about multipartite entanglement. But I mean, we remember that in the bipartite case, so if you have bipartite pure states, then we fully understand the conversion. So we fully understand the single copy conversion by the Michael Nielsen paper. We also fully understand the multipartite rates, not the multipartite, but the asymptotic rates for bipartite setting. Yeah, so this is basically the transformation rate in the bipartite case. And but as long as you go to multipartite setting, so even if you look at 3 qubits and you have a pure state of 3 qubits, then you neither know which other pure states of 3 qubits it can be converted into, nor you know the rate. So, and this is like in general. For some special cases you do know, but in general you don't, right? So, and this is a bit disappointing, right? Because, well, I mean, so it seems that like there should be something that could be done about it, yeah? And essentially, this is the main question here. The question that I ask here is, can we resolve this problem by relaxing the set of LOCC operations in the multipartite setting? So can we relax the LOCC set in such a way that we get a nice expression and simple expression for the asymptotic transformation rates? Yeah, and yeah, basically this leads us to what I call asymptotically entanglement non-increasing operations. And yeah, let's again look at so you could imagine this blue set to be the set of multipartite entangled states. And so basically, I call an operation epsilon entanglement non-increasing if it increases the relative entropy of entanglement of any state by at most epsilon. So if that holds for all states, then the operation is epsilon entanglement non-increasing. Yeah, and ER here is the relative entropy of entanglement. Then I call a sequence of such operations, I call it asymptotically entanglement non-increasing if for any epsilon there at any capital N there is a small n which is bigger than capital N, such that the sequence is epsilon, such that lambda n is epsilon entanglement non-increasing. So in other words, we require for the sequence that it well, that for n large enough, it increases the entanglement only by an arbitrarily small amount, you know? Because this should be for any epsilon. I mean, for those who are familiar with the papers of Martin and Fernando, this is somewhat similar, although not exactly the same as their asymptotically non-entanglement operations. Yeah, and now we can also talk about conversion rates. So a state rho can be converted into a state sigma via this asymptotically entanglement non-increasing operations if for any epsilon and delta and n, there is a small n bigger than n, such that lambda n is epsilon entanglement non-increasing and this condition is fulfilled. So basically, lambda n maps n copies of rho into r n copies of sigma with error at most delta. Again, this is similar to the standard conversion rates, but like tailored to this setting. Yeah, and basically the optimal conversion rate in the setting is the supremum over all such achievable rates. And what you can what is not very difficult to see is that this this rate, the rate over asymptotically entangled non-increasing operations, is definitely bigger than this R here is the standard rate. I mean, just because this is a more larger set of operations, and also what one can also show is that this rate is upper bounded. So for any two entangled states, it's upper bounded by the fraction of the regularized relative entropies. So this that means that this setting fulfills at least this basic assumption that I was mentioning a few minutes ago, that the rates are bounded, right? So so it leads to a non-trivial theory. So where entanglement kind of has a meaning because the rates are bounded. Good. And now, well, I promised you some results about multipartite systems, but actually so far I essentially talked only about bipartite setting. So I now define multipartite asymptotically entanglement non-increasing operations, and I define them as those which basically do not increase the entanglement or have a kind of a controlled increase of entanglement in all bipartitions. So let's say you have a multipartite system and you take a split T versus T bar, take any split, any bipartition of your system, and then we require that our operations increase the entanglement in this bipartition by at most epsilon. And if it's true in all bipartitions, then the operations are epsilon entanglement non-increasing in the multipartite setting. And and essentially, the asymptotically entanglement non-increasing operations are then defined as in the bipartite setting, it needs to be with respect to any bipartition. So I hope the definition is clear. And so now we can go to the result. And the result is, as I promised, is a nice expression for the asymptotic transformations rate between pure multipartite states. So for any two states psi and phi, the optimal conversion rate via asymptotically entanglement non-increasing operations is the minimum of s psi t divided by s phi t, where t is is any subsystem. So if you have 3 qubits, for example, then t you would take the minimum over the first, the second, and the third qubit, and so on. Like for more particles, you just take the minimum over all subsystems. So it is remarkably similar to the bipartite case, right? And so let me tell you how this can be proven. Well, as I already mentioned, the asymptotic this rate here is upper bounded by the fraction of regularized relative entropies. So that means that, I mean, this is definitely smaller than this. Yeah, I mean, so this is an upper bound, and now we just need to prove that it's achievable, right? So that there is a protocol that achieves this. And this can be done by introducing a sequence of operations of this form. So essentially here we project rho onto n copies of psi, and here we attach like basically, if this projection is successful, if we get this outcome, then we replace our system by Rn copies of phi. And here, for technical reasons, I need a flag here 0, 1. This is, you can think about it as being a particle in Alice's laboratory. And basically, in the other case, so if we get the other outcome, we replace our system by some separable state. It doesn't really matter which state it is, just some separable state. And and so what you can now easily see is, now if you apply this operation onto n copies of psi, right? So if rho is n copies of psi here, then you get a 0 over here. So you just get Rn copies of phi. So this operation maps essentially n copies of psi onto Rn copies of phi, which is already a nice feature. And now what what you need to prove is that this sequence is asymptotically entanglement non-increasing whenever the R fulfills this property. So you remember R was related to how many copies of phi you have here. So whenever R fulfills this sequence is asymptotically entanglement non-increasing, and the proof of that is what's quite complicated, and you can find it here. And that means, so after you have proven this, that means that in the multipartite setting, this sequence is asymptotically entanglement non-increasing in every bipartition whenever this inequality is true for any subsystem T. And this actually together implies that you can achieve a transformation in that rate. So the map that achieves this transformation is actually this lambda n, right? So you can achieve the transformation with this rate in the setting of asymptotically and non-increasing operations. Let me now tell you a few applications of this. That means that in the setting of asymptotically non-entanglement operations, you get in some cases you get the reversible transformations between pure multipartite states, and this is whenever the transformations are reversible whenever the state psi and phi fulfill this for any subset T and T prime. So if for all subsets T and T prime this inequality is full, then you have reversibility. And that, for example, means that you can reversibly convert GHZ into W states. And well, the conversion rate from W into GHZ is actually here the binary entropy of 1/3, which is 0.92 in that setting. Yeah. And I remind you that transformation between these two states is not possible reversibly via LCC. Another interesting case is if you have like 2 copies of GHZ and 3 copies of an entangled of a singlet, then it was also noticed quite some decades ago that via LOCC you cannot reversibly interconvert them, but in this setting you can. Another interesting observation here is that in this setting you can, if you have a tripartite pure state, you can always reversibly interconvert it into bipartite pure states shared between all the parties. And basically this is also a question that has been raised many years ago, whether such a conversion is possible or not. And this is related to what is called reversible entanglement generation sets. So like what is kind of the smallest set of states that can reversibly be interconverted into any other state. And essentially in the tripartite setting, singlets, bipartite singlets form a reversible entanglement generation set again, I should add, in this setting, because in the LOCC framework, they do not. So singlets are not enough to reversibly generate all tripartite states, but in this setting, you can get any tripartite pure state from singlets reversibly. So I'm already at the end of my talk. So what I have showed you is that by relaxing the set of LOCC operations, we can get a solution of asymptotic state transformations between pure states in the multipartite setting, and the asymptotic rates are given by an expression that is very, very similar to the bipartite setting. So basically, we take entanglement entropy fractions in all bipartitions. In this setting, we can reversibly interconvert GHZ into W states, and in the tripartite setting, singlets form a reversible entanglement generating set. So every tripartite pure state can be reversibly obtained from bipartite singlets. And yeah, if you want to know more details, you can look at this paper on the archive. Thank you.
Yeah, thanks for the very nice talk. Any question?
In your result, with the asymptotic entanglement-nonincreasing map, then the multipartite properties almost disappeared and only the similar to the bipartite property recovered. But if we employ not the asymptotic but the conventional entanglement non-increasing map, I think we cannot expect such a similar result to use. So why the asymptotic as property removes the multipartite specialty? Intuitive explanation?
I'm not exactly sure what you mean by like a non-asymptotic. So you mean like if we say we only look at maps that map separable states into separable states, but like non-asymptotically, but exactly, yeah. Yeah, I think. I mean, I'm not sure what happens if you do in a multipartite setting. Yeah, but I guess you need this kind of epsilon thing to be able to get to be able to get the optimal rates, because otherwise, if you require it to be exactly non-entangling, although I didn't study this problem here, but I guess you will not be able to get the rates. At least from my intuition, that's what I expect.
Any other question?
So I'm wondering that under this entanglement and non-increasing operations, so previous monotones are still satisfy monotonicity, or if all if previous such as a concurrence or some entropy of entanglement.
Well, this is we're talking about multi-party entanglement. So I mean, probably so concurrence is, at least to my knowledge, is only bipartite, right? So then yeah, we could ask about multipartite monotones. I think probably some monotones will still be monotones, but not all of them, because we're here looking at a more general set of operations. I think some monotones which are monotonic and our LOC will not be monotones here anymore. That's, but I didn't study that in too much detail. So.
Yeah, okay. Yeah, thanks very much.
Yeah, so yeah, to adding to his question, like there's some monotones like GME is there based on concurrence, and there is Tangle also is there based on negativity to calculate this multipartite entanglement. But for a genuine multipartite entanglement, most of the monotones fail. So this Tangle is best one. So as far as I know, so I have a question like here, as you said in slide number 10, that the entanglement non-increasing operations are okay. So that when you calculate the rate for these GME states, so I mean multipartite setting the entanglement. So I would like to know like whether this entanglement is like there for all bipartition, or is it like entanglement between just a bipartition? Like because the entanglement cannot be there, like may not be there for all bipartitions, right? Like for example, a G is there state.
Yeah.
So there exists maximal entanglement for all bipartition, right? So if we trace out one of the like subsystem, still we'll see entanglement. But there exists some states. If we take a trace out one of the subsystem, then the entanglement is lost. That means the entanglement is not for all bipartition, but for some bipartition. So I just would like to know, okay, like whether this work is for for just a bipartition or for all.
Well, I'm not sure if I don't understand your question. Maybe we can talk about it in the coffee break. So
okay, okay, sorry.
I cannot answer it because I fully understand.
Okay.
Yeah, so any other question? Actually, Alex, I have one. I think it's really nice to have the reversibility considering the non-physical operations. But if we really seriously like consider how to implement the asymptotic non-entangling operations, do you think how much entanglement we need? Will it be asymptotically vanishing, or will it be like a lot?
Well, I think, well, we can, I mean, yeah, you could ask the same question about not like just the standard non-entangling operation. So I think nobody really knows that. I mean, if you say how much entanglement you need to implement, then you probably mean that, for example, you want to implement them by using LOCC plus some entanglement. But I'm not sure if that's the.
Or maybe we consider the easier question, so like entanglement plus non-entangling operation.
Yeah, I didn't look into this, but I don't know, but still, I wouldn't say that they are not physical. They are physical in the sense they are CPTP maps, and yeah, they might be difficult to implement, but also, I mean, also LOCC are difficult to implement because for LOC you need to control to control infinitely many local qubits, which is very difficult also. So maybe, yeah, I would say they are maybe a little bit more complicated or quite more complicated than LOCC, but I wouldn't call them unphysical, right? Because they are CPT maps. I mean, or compared to the maps of the previous talk, maybe they are more physical.
Yeah.
Okay, thank you.
Okay, yeah, thanks. So any other question?
Can I ask one?
Yeah.
Hey, so your condition is asymptotically entanglement, no increasing cooperation with respect to relative entropy of entanglement, is that right? And say that Brando-Planio talks about the asymptotically entanglement non-generating operation was the D max, right? So like, is there any, of course, like you're talking about the multipartite relation and so forth, but is there any relation between asymptotically entanglement generating the D max and your setting?
Well, actually, the maps of Martin and Fernando are this asymptotically entanglement non-generating. They are also asymptotically entanglement non-increasing because just by this condition that the robustness of entanglement can only increase by epsilon, you get this kind of thing. You get this condition you get from that, but
With relative entropy.
yeah, you then get that the relative entropy cannot increase. But I essentially, for proving this, I first tried to assume only a similar condition for the robustness, but I didn't manage to prove it by using the robustness alone, so I needed to go to this condition. So it is, in principle, it's a more general set of operations for this, under this condition, I was then able to prove that rates. But eventually, it can also be proven by assuming a non-increase on the robustness, but I'm not sure.
Thanks.
Okay, if we do not have any further question, let's thank both of the speakers.